Jesus and Dan to really, oh, I got a notification, okay. Thank you to Jesus, Lucia, and Dan for this opportunity to really literally speak to people all around the world. I never did this before, so it's really exciting to do. And before I start doing mathematics, I just want to wish Thursday's speaker, Aisha Borat, a happy birthday. I wasn't about to forget this, okay. Yes, I'm talking about spherical complexities and closed geodesics, which on the first side has nothing to do with TC, but I will define invariants called spherical complexities that are defined in a way similar to TC, which are then used for calculus of variations and to tackle the closed geodesics problem, which I will elaborate upon in a moment. So to start with, I want to go way back in time, way beyond the invention of TC, and not back to Adam and Eve, but to Lustanich and Schnirelmann. And I want to explore the relation between Lustanich-Schnirelmann category and critical points, because that was the initial purpose of Lustanich and Schnirelmann to invent their category and to study this notion of category. Namely, there's the famous celebrated theorem of Lustanich and Schnirelmann. The finite dimensional version is from the two authors in 1934. The version I'm stating here is a formulation by Palais from 1965. Namely, if we have an arbitrary Hilbert manifold M, and we have a function on this Hilbert manifold which is continuously differentiable of class C11, which means continuously differentiable and locally Lipschitz bounded derivative, although this assumption can also be removed later, which is bounded from below and satisfies the Palais-Mail condition with respect to some complete Finsler metric on M. If you don't know what a Finsler metric is, think of a Riemannian metric. That's fine for this purpose. Then the number of critical points of such a function is bounded from below by the category of M. So I'm following Helen and Peter in using the unreduced version of category TC and whatever comes. So everything is unreduced here in this talk. So this is now a topological quantity which gives a lower bound for the number of critical points for arbitrary functions which satisfy these quite weak conditions. There's also another theory going this direction is Morse theory, which requires much stricter assumptions on the function that are studied. So, but this is in general the way that Lustanich and Schnirelmann saw this invariant and that they studied this. Just a remark, this is not by far not the most general version. There are several ways of relaxing these conditions. For example, Klapp and Puppe in the 1980s have worked out some generalized Palais-Mail conditions which relax this a bit. And there's a nice topological description by Rudiak and Schlenk, which extends the theory to kind of fixed points of self-maps of topological spaces, where critical points can be seen as fixed points of gradient flows. And so generalizing it in that respect. But this is the version I want to just state today. Okay, I want to briefly go through the method of proof of this thing because this is quite instructive. We have a function which satisfies these nice properties on M, and we denote by F upper A the closed sublevel sets of this function with respect to some value A. And then we have the subspace categories. So category with respect to M of subsets of M. So we need to cover subsets or subspaces by open subsets whose inclusions are null homotopic in M. And we can use these categories of subspaces and some minimax methods from calculus of variations to basically show two different things. The idea is we start with some small sublevel set and then increase the sublevel set and see what increase the level and see what happens when we increase the level. First of all, the simplest observation is if some interval contains no critical value of F, then raising the level from A to B, so from the lower to the upper bound, does not change this relative category. So nothing happens in this case. Whenever we cross a critical value, something happens. Namely, we know that the category of this new sublevel set with respect to the critical value is bounded from above by the category of some slightly smaller sublevel set. So that's for sufficiently small epsilon so that there is no critical value in between C minus epsilon and C. Plus the subspace category of those critical points that lie on this critical level that just appeared, so that we just studied. So we see that this increases with each critical level, and we know that this is one or bigger, so we have some contribution for this estimate coming for each critical level. If we combine these observations, we see that in every sublevel set, the category of this thing is a lower bound for the number of critical points that are contained in the sublevel set. And if we know that A rise the level set to infinity, then we obtain the theorem globally, so we get the result that we want to have. So in a very naive question is now if we can tackle closed geodesics with Lustanich-Schnirelmann theory and with this immediate approach of Lustanich-Schnirelmann theory. And I will explain this for a tiny bit. So we have a closed manifold and we have a Finsler metric on the manifold. the Finster metric is a function, smooth function, not smooth, continuous and function on the tangent space, which has no negative values, which is something like a fiber-wise norm. So it behaves very roughly like a norm on each tangent space. If you just want a simpler example, just think of the Riemannian metric. A Riemannian metric is an inner product on each tangent space, and this induces a norm on each tangent space. And in this way, we can define a Finster metric. So this would be a special case for Finster metric, which can be generalized to have some properties, which I don't want to record today because this would be a bit too much. With every Finster metric, we can associate an energy functional on some space lambda m that I will introduce momentarily, which is a space of loops. And on this space of loops, we can just consider the function that we get by integrating the square of the Finster metric along the loop. So into the Finster metric, we insert the loop and the derivative of the loop. I will say a bit more of this. This comes from the definition of lambda. I will go through this soon. So we integrate this f squared along this loop, and this is then the function that we obtain. So this space lambda, this is sometimes also denoted by h1 s1 of m. This is a subspace of the space of continuous loops, so of the free loop space, which actually has the same homotopy type as this, and this is a Hilbert manifold. And actually, you can use this as a black box. This is kind of a Hilbert manifold model for the free loop space of a closed manifold. Just if you want to know the precise definition, it's is locally modeled on the Sobolev space, H1, S1 to Euclidean space of the right dimension, or W1, 2, as you usually note these Sobolev spaces. So we consider all loops that in local coordinates look like elements of this Sobolev space of loops. So, okay. It turns out that this energy functional is really nice in the sense that it has this property C11, so it's the right differential regularity properties, and it satisfies the Padé-Smale condition. In the Finster case, this was shown in 77 by Mercuri. And the interesting thing is now that the critical points of this functional are the closed geodesics of F and the constant loops. If you don't know what a closed geodesic of a Finster metric is, you can take this as the definition, so a non-constant loop, which is a critical point of this function. And the question is now, if we have this, can we use the Luesner-Knielman approach to obtain lower bounds on the number of closed geodesics of F? And I've put quite some adjectives here in front of these closed geodesics. Mm-hmm. First of all, we want non-constant closed geodesics. I mean, constant loops are not interesting, so this is not what we want to study. And geometrically distinct, I've written here. The idea is, if you take a look at this functional, we have a standard S1 action on the loop space by shifting the time parameter. So just by adding a constant time parameter to the loop and obtaining a new loop this way. So I think Helen called this yesterday also the rotation action that we have on the loop space. So if you take a closer look at this integral here, this is invariant under this action. So we really have an S1 invariant action, which means that the critical points of this function will occur in orbits. So we always will have orbits of critical points. And of course, we want to count the number of orbits. By geometrically distinct, I first of all mean that either they are really not in the same orbit, or that they are not in the same orbit. And something that also can happen is that we have iterates of loops. Namely, if we take a loop and run through the same loop twice or multiple times with increased speed, so we get parameterized this by the same interval, then we again get a closed geodesic. So with every closed geodesic, we obtain an infinite number of closed geodesics, simply the iterates of the one we started with. So we are, of course, not interested in these iterated ones as well. And if I write geometrically distinct, I mean that I want the number of geodesics which do not lie in the same orbit or which are not iterates of each other. So this is what we actually want to study. And so it turns out that applying this Luesner-Knielman theorem is then a very naive wish, because there are several problems that occur from these properties I just mentioned. Namely, first of all, we have the constant loops among the critical points, which we want to disregard in the closed geodesic counting. And we know that every constant loop, that's by definition of a Finster metric, every constant loop has energy 0. So for every non-negative value, we have all constant loops in the sublevel set. So the number of critical points, if you write it like this, is always infinity. So this is, of course, bad. So this means in this counting procedure that I described in this proof of Luesner-Knielman, we would have to know what the subspace category is for the space of constant loops in the free loop space. And this is not clear, and there is no general answer to that. So this gives problem. So we cannot, if we disregard the constant loops, we don't know how much we have to subtract from the inequalities and cannot really handle this. And of course, this thing that I said that the critical points come in orbits, but the problem is that such an orbit may have subspace category 1 or 2. So also we cannot, we don't know how much every orbit is contributing to this counting procedure. So this doesn't really work. And the idea that I want to carry out today is that for a setting like this on the free loop space, we can replace the subspace category function, so which takes a subset of lambda m and associates some integer with it, some positive integer with it, by a different function which has similar properties, which turn out to be more useful or more appropriate for this counting procedure for functions on the loop space. Before I study my approach, let me just mention that there are also several similar approaches to G invariant functions, and one of them was mentioned by Helen in her talk yesterday, namely the one of Klapp and Puppe, who did some work on this invariant function. They particularly studied the closed geodesics problem as well with respect to this S1 action, and obtained some results by this that I don't want to talk about today. And Thomas Bartsch has a nice Springer lecture notes volume on kind of variational problems with symmetries and topological approaches to this. So there are which basically also extends the Klapp and Puppe or uses the Klapp and Puppe approach of these equivariant formulations of category. What I want to introduce today are these new invariants, these spherical complexities. And they are now defined in a similar way to TC. I think the sectional category was already mentioned by several speakers, so I won't elaborate on that too much. So the sectional category of a fibration is the minimal number of domains, open domains that we need to cover the base space, such that over each of these bases we have a continuous section of the fibration, a local section of the fibration. Now I want to consider a particular fibration that turns out to be useful in this setting, and I want to generalize. Instead of loop spaces, I want to study sphere spaces for arbitrary spheres of arbitrary dimension. And for this purpose, I consider a topological space X and some number n. And let Bn plus 1x denote the space of continuous Bn plus 1 balls in X. Then I consider the space Snx, which contains all continuous n spheres in X, which are null homotopic. And I know that, or it's easy to see that a continuous map from the sphere to X is null homotopic if and only if it can be, if it's the restriction of some map from the ball, so it can be extended to a map from the whole ball to X using the homotopy, for example. So these here are really the kinds of maps from the sphere that are obtained by restricting maps from this ball space. And this is, in fact, the fibration that I need, namely the n spherical complexity of X, as I call it, is given by the sectional category of the fibration Rn, which takes a map from this ball space and maps to the sphere space simply by restricting a map from the ball to the boundary sphere. So we search for open domains such that over each of these domains we can continuously, with respect to the C0 topologies, kind of fill spheres by balls. That's the main idea behind this thing. It turns out that's the thing of the whole space, that this number here will it's quite likely to be infinity, so it's not that useful, but it becomes very useful if we consider subspaces. Namely, for each subspace of the sphere space, we consider the relative version of this, so the sectional category of the restricted fibration, we simply restrict to the part of the fibration which lies over A, and then define the sectional category of this thing. Okay, and these invariants turn out to have nice properties. First of all, and that's kind of the justification that I'm talking at this conference, if we put n equal to 0, we obtain the topological complexity. This is so in that sense, I am generalizing TC in this way, because if n is equal to 0, we have maps from the 0 sphere to X, which is nothing but the map, 2 points, so we just get X times X. And the space of one-dimensional balls in X is nothing but the path space, and the restriction is then precisely the fibration which evaluates the path at its ends. So this is really generalization of TC. Then I want to study what happens with respect to the problems that occurred in this counting procedure I just described with category with respect to the closed geodesics. And there I need X to be a metrizable absolute neighborhood retract. So this is just a technicality. For example, if you don't know what an absolute neighborhood retract is, a locally finite CW complex is enough for what I'm doing now. And so first of all, we had this problem of constant maps. So of course we have a map which goes always in every dimension. We go from X to the space of spheres, which simply associates with each point in X the constant map from the sphere which maps everything to X. And it turns out this spherical complexity of the subspace here is simply 1 always. And the proof, I will skip the proof, but it fits within one line. Actually, with every constant sphere, we need to associate the constant ball, which maps to the same point, and can define a section of this fibration in this way, which is obviously continuous. So this is good news. So we know how to count the constant elements in this counting procedure. And now we will come to group actions. And here on these sphere spaces, so for arbitrary dimension, it becomes a little more complicated than for loops. Namely, we have an action of On plus 1 always on these spaces. Namely, if we consider the n+1 ball just as the unit ball in Rn+1 and the n sphere as its boundary, we have every orthogonal matrix is acting on this sphere, respectively on this ball. And we can just use this action of reparameterization here. Namely, we just insert the action in by multiplying the parameter of the loops or the element of the sphere or the ball by this by a matrix. And I just added a -1 here to make it a left action instead of a right action. So we have this reparameterization action, and there are quite some functionals which are invariant under this action, or actions of subgroups. And so if here is the nice thing that these spherical complexities behave nicely with respect to this action. If we take a closed subgroup of On+1 and just some arbitrary element of Snx, and that G gamma denotes its isotropy group, so we are interested in the relative spherical complexity of the orbit of this thing. And there are two cases in which this is, has a very simple answer, namely if the isotropy is trivial, so the group acts freely on this element, or if we are in the one-dimensional case, then the spherical complexity is always, of the whole orbit is always 1. So if in the trivial case, it's easy to see. If we just take gamma as an element of this orbit and take a ball filling gamma by rotating or modifying gamma with respect to this orthogonal action, we just modify the corresponding ball as well. And since we have no isotropy, nothing can go wrong. So we can define a thing on the whole orbit in this way. And in the one-dimensional case, it becomes a bit more complicated, but it's well, you have to check the technical details, because the isotropy groups that can occur here are all finite. Either it's the whole group, or the whole orthogonal group, or it's a finite subgroup, and these things can be dealt with independently. And so it's where you can write down explicitly solutions of this thing. Okay, so using these invariants now and these properties, I can define a Lustanich-Schnielmann type result now, where I use the properties I just sketched on the previous slide. Namely, if I'm in the sphere space setting, so I have a sphere space Snx of non-homotopic spheres, and I have a subset of this, which is a Hilbert manifold, which is invariant under this reparameterization action. And so that they have a function which has the nice differentiability properties, C11 on the Hilbert manifold, which is invariant under reparameterization as well. I want to count the number of G orbits in the critical points, in the set of critical points of F with respect to sublevel A, which I denote by nu of FA, this count. So if F now behaves again well with respect to this Palais-Smale condition, so this is just a technical condition that we need for the minimax procedure that's underlying this. And then if F is constant on the space of constant spheres, which is, for example, a reasonable assumption for this, the energy functionals, where the energy functional of a constant, the energy of a constant loop is always 0. So if this is satisfied, and if we have these isotropy conditions fulfilled, so if either G acts freely on the critical subset, which is in the sublevel set, or if we're in the one-dimensional case, then we get this nice count, namely this relative spherical complexity of the sublevel set is a lower bound for this number of orbits +1. This additional +1 that was not occurring in the original Lustanich-Schnielmann theorem, this is due to the constant loops. So this is the contribution here. Okay, so we have some method now of how to estimate the number of these things in this general setting. And let me just quickly state this for closed geodesics in this special case, because this is the one-dimensional case where this isotropy condition is always fulfilled. Again, we have this energy functional of a Finsler metric on a closed manifold and this Hilbert manifold lambda m. And this time we have to intersect it with S1m, so with a space of contractible loops in M. Which doesn't matter, which doesn't hurt our argument, because this is simply a connected component of lambda m. So this will be again Hilbert manifold. So if we consider this restriction here and apply the previous theorem, then the number of SO2 orbits, so the rotation action that we had is an S1 or SO2 action that we studied of non-constant, and now we're studying contractible closed geodesics. That's the setting here, because we are taking this intersection now. The set of contractible closed of orbits of contractible closed geodesics in the sublevel, so of energy at most A. We know that this number is bounded from below by the spherical complexity of this sublevel set EFA -1. So this is really giving us now some estimate for this number of contractible closed geodesics. And as we know that invariants that are kind of defined using sectional category, they are hard to compute, but it's always possible, or it's possible to find some computable lower bounds for this. So to use cohomology methods in this case to find lower bounds, for this thing. Oh yeah, well, sorry, one more thing. That's just for those who know, if the Finster metric is reversible, this is some kind of symmetry condition for the Finster metric, which is not always satisfied. This is a special situation in which the functional is not only invariant under this rotation action, but under a full O2 action. Then everything I'm saying goes for the O2 orbits and not only the SO2 orbits. But if you don't know what this is, then you can just forget about this. This is just a technicality. Okay. Oh yes, and what I forgot to mention, this counting also still doesn't distinguish the iterates of the same prime closed geodesics. I said, so this is now the number of orbits, but again, iterates of closed geodesics are closed geodesics, and this doesn't recognize if a geodesic is an iterate or not, so we still have to find a way of how to get rid of these iteration issues. Okay, so to define lower bounds for these spherical complexities, I want to apply some cohomology tricks, and I want to go a bit into detail here because I think this is kind of most interesting for this topological-minded audience. So first of all, we have a connection between sectional categories and the cup length. So the aim is we want to find computable lower bounds on my new invariants here using cohomology. And just some notation, if we have a space and a coefficient ring and some ideal of the cohomology ring of X with respect to these coefficients, we just let CLI denote the cup length with respect to this ideal or the nilpotency of this ideal. So the biggest numbers that are such that we have a product of R non-vanishing classes, non-vanishing product of R classes of positive degree inside this ideal. Okay, and this thing that already was used by Michael, I think, in this talk, and should be known to most of you. If we have a fibration, P from E to B, and the sectional category of this fibration, we get a lower bound by studying the cup length that is obtained in this ideal of the pullback of the fibration in cohomology. So this as an ideal in the cohomology ring of the base space. Here, since I'm using the unreduced definitions, there's a +1. Okay, this is nice direct estimate. And if we apply this in the situation of spherical complexities, you can use this estimate and then play along with cohomology a bit, where I don't want to go too much into detail, but just you basically only need the long exact cohomology sequence of S and X relative to the space of constant spheres, and obtain the following estimate. If we take some subset here, and that iota denote the inclusion of pairs A and the relative to the empty set, and S and X relative to constant spheres, to let this be the inclusion, then the spherical complexity of A is bounded from below by the cup length inside the image of iota upper star. So the cup length of all classes in this subspace, which come from classes here in this cohomology group, so in the cohomology of the sphere space modulo constant loops, and again +1. So, and if you keep in mind that the main example we are studying is that A is a sublevel set of a function. So this is basically, we're studying cohomology classes that appear in sublevel sets of function. And this is always a very intricate question, at which sublevel a cohomology class starts becoming visible or not. So this is also some quite natural question appearing also in topological methods in variational calculus. The problem, of course, is that the cup product might not be that interesting or hard to compute, since we are dealing with a sphere space and we might have issues with this. And yeah, or it might be just useless, as it turns out. And I've just searched for a simple example, namely it's well known, I don't know who established this first, that in rational cohomology of the free loop space of S2, so not that, so LS2 should be the free loop space, relative to constant loops, the cup product is just trivial. So in this case, this estimate would just be useless to estimate our numbers here from below. So we have the problem that cup product is, while in principle we can use it here, it just might not be useful. So the idea is now to improve these cup length bounds by associating weights to cohomology classes. And this is a very general way of going that was also done in several different settings, and I want to explain a bit about this. So for this, I have to go a bit into detail here, and namely into the things underlying these studies of sectional category. If we have two different fibrations over the same base space B, P and P prime, we can form the fiber-wise join of P and P prime, which I denote by join with an F as an index for fiber-wise. So the fiber-wise, this is again a fibration over the same base space, and it turns out this space has the fiber over each point in B. We get the join of the two fibers of the individual fibrations that we had before. So this topological join of these spaces, this gives the new fibration. So this is the one of the main things underlying here. And what we can now do is to take one fibration and define a whole family of fibrations by iterating this fiber-wise join construction. So I want to define fibrations PR for each R. Just recursively, I say the first of these fibrations should be the original fibration P itself. Then I take the rth fibration as the fiber-wise join of P and the R minus first. So the P2 would be the join of P and P. And then I join another copy of P, another copy of P, and so on, and so on, and so on. And so I get an infinite family of fibrations. And one of the, basically, yeah, I think maybe the main result of Schwarz's seminal paper on sectional category is that the sectional category fibration is the smallest number such that the fibration PR, the rth of this thing, has a global section over the whole base space, a global continuous section of this. So this is where these fiber-wise joins are connected to sectional category. Using this, we can now define this cohomology weights with respect to a fibration and a coefficient ring. So this was first done for the Schneermann category by Fadel and Husseini in 1992, and then kind of improved and extended by Rudiak in 1999, who slightly varied the construction to make it work a little more nicely with respect to, it had better topological behavior, so to say. And then the general case for sectional category rate for arbitrary fibrations was carried out by Faber and Grant in 2007. So if we have a reduced cohomology class, so a class of positive degree somehow, which is non-vanishing, we define the weight of the class with respect to this fibration as the biggest number R, the biggest number R such that the pullback of this class by the rth fibration is vanishing. And remember, where the sectional category is the number such that where PR has a section, a global section, and the necessary condition for PR to have a global section is that PR upper prime is injective. So if we have such a class which is kind of in the kernel of PR upper star, this destroys the injectivity already. And this is the connection that we get to sectional category. Namely, we get that if we take, that's two of these classes, such classes be given. First of all, if we have a class U which has weight K or bigger with respect to the fibration, then its sectional category is K plus 1 or bigger, simply by this injectivity argument that I just gave. And the most important property for this next thing what we need, it is super additive with respect to the cup product. So the weight of the cup product of two classes is bounded from below by the sum of the weights. So this goes for every fibration, and this is very useful in that sense. And this is really improving this cup length bound. Namely, if let's assume we have K as the cup length in the ideal K, the kernel of P upper star, and we have K such classes whose product is non-zero. Then we know that using these two in combination, that the sectional category is bounded from below by the sum of the weights plus 1. And since this is then 1 or bigger, this really improves this cup length bound. So this sum is K or bigger. So we can use this to beef up the cup length estimate. Okay, so in our particular setting, we have this fibration Rn upper star, the fibration Rn, which restricts a map from the ball to the boundary sphere. And so we want to find classes of weight 1 or bigger. So we need to find cohomology classes in the kernel of the pullback of this fibration. And it turns out there's a nice construction procedure to this. Namely, if we have a space and we consider the sphere space as n of x, and the evaluation map which evaluates, which takes an element of Snx and a point in Sn and evaluates the map at the point P, we can use this then to construct a class. Namely, there's a procedure. We take, I call this map Zn. We take a cohomology class of x, an arbitrary non-vanishing class, and obtain a class in degree k minus n by simply pulling back to the fibration and pulling back with respect to evaluation, and then take the slant product with the fundamental class of Sn. So roughly speaking, we pull back with the evaluation and mod out the parameter space here in this way. Then it turns out that this class is always in the kernel of the pullback of this fibration. But of course, there's one obvious issue. We don't know if Zn of sigma is vanishing or not. So this might be a good way to construct classes that we need, but we might have problems with this vanishing. Nevertheless, in the one-dimensional case, so if n is equal to 1, and if the space is simply connected, then you can actually derive that this map, Z1, so which is then defined on the reduced cohomology of X and goes into the cohomology of the free loop space, that this map is actually injective. This is kind of a special or very particular case of a theorem of Jones relating free loop space homology and Hochschild homology. But just so you know, this is actually useful, this construction. So we get something non-trivial out of this. Okay, once we have classes of weight 1, we want to have classes of weight 2. And there's a nice construction method for this, which generalizes things that was carried out by Mark Grant and myself in the paper on the topological complexity of symplectic manifolds in 2018. And I've put Mark's name here in bold letters because actually what I'm doing on this slide and the next one is almost everything is due to Mark's ideas. So I don't claim any originality on this. Namely, we know that the fiber-wise join is of a fibration with itself is constructed as a homotopy push out of a pullback, or another way to put this is as a double mapping cylinder. Namely, the following: we first take the pullback of 2 copies of the fibration and take a pullback space Q, and now take a homotopy push out of this corner here that appeared in this diagram. So we obtain a diagram of this style, where we obtain a homotopy push, where this is supposed to be a homotopy push out, and this then turns out to be this fiber-wise join of the 2 fibration. And not only that, if we take the map that's then induced in here between this new fiber-wise join and the base space, if we have put in the maps P like this induced map here, this is then the fibration P2 that was defined before. So this is the way we obtain this. And this is good news, because as a homotopy push out of a pullback, there's a general construction that this thing always has a Meyer-Vietoris sequence. So we get a nice cohomology sequence looking like this. So the top row here in this diagram, the Meyer-Vietoris sequence, where the role of the union, roughly speaking, is the fiber-wise join here. So this homotopy push out. Then the 2 components of this are both copies of E. So this is the term appearing here. And this is the third term in the sequence. We get kind of the role of the intersection of the 2 parts of this, which is played by the pullback here. So this is the pullback space. Now, what does this help? We want to study classes from here and want to, so from the cohomology of the base space, and want to study if they pull back to 0 or not under this map here. So we get some commutative triangle here by using the maps from the previous push-out diagram. These are the maps induced in this push-out procedure. And here we get twice the pullback with P, so with the fibration itself. And if we assume that the cohomology class has degree 1, we know that this pullback here is by definition then vanishing. So we know this is vanishing, which in turn means that the composition of these 2 arrows here is vanishing. Which means if we pull back this class here, we don't know if the class itself is already vanishing, but we know it lies in the kernel of this map here, which I haven't named. So we know the map is in this kernel, and by exactness, we know it's in the image of the connecting homomorphism. So we know that the pullback here has some pre-image over there in the space of the pullback. And this is helpful indeed, because this space, this homotopy push out, this might be a very complicated space whose cohomology is not easy to determine, but this pullback is often much easier because there is no join construction involved in something. So it turns out that there we might get a nicer result. So we want to find classes which pull back to 0. And we know that if we have classes which already lie in the kernel here, we know that they lie in the image of the connecting homomorphism. And so what we then want is to find a pre-image under the connecting homomorphism. So we want to find some alpha u in this cohomology group, which maps to the pullback of this class here under the connecting homomorphism. And if we then can show that this class alpha u is already vanishing, then of course we know that the pullback is vanishing, and then we know the class has weight 2. So the question is now, what does this class look like? So how can we determine such a class alpha u, which has this nice property? And this we want to study in our setting. So first of all, we go back to the special case of this fibration Rn, which goes from balls in X to spheres in X. And there, this pullback is by definition just very simple. The pullback of 2 copies of the fibration. It means we have 2 maps from the n plus n ball to X, which coincide on the boundary. And this is just nothing but a map, but the 2 hemispheres of a map from the sphere in 1 dimension higher because of this coincidence here. So this space is actually easily seen to be homeomorphic to the continuous maps from the spheres in dimension n plus 1 to X. So here we can really explicitly determine the pullback. So the Meyer-Vietoris sequence in our case, if we abbreviate this join by E2, takes this form. So we have in the central term here is the cohomology of E2. Here we get the cohomology of the total space of the fibration, and here we get the cohomology of this mapping space C0 from Sn plus 1 to X. So if we now take this construction that I carried out, so we take a class on the space X and then find with it a class of weight 1 by this evaluation pullback that I carried out in this cohomology of Snx, what is now the pre-image of the pullback here under the connecting homomorphism? So what is this associated class alpha with respect to Zn of u? And it turns out that this can be explicitly determined. Namely, we can compute in this case that if we have a class which is in degree k, which is at least n plus 1, that this class alpha with respect to this constructed class is the pullback of the evaluation modulo sphere as well, but this time in 1 dimension higher. So here we have the evaluation which takes n+1 spheres and in X and evaluates them on each in the point in n+1. So the difference is here that now the dimension is 1 higher. And of course, here we take all continuous maps, not only the null homotopy ones. So this is then the class that we really need. And so we know that if this class here is vanishing for some reason, then we know that our class Zn of u that we are using here has weight 2 or bigger. And then you can play around with this and use this lemma and this Meyer-Vietoris argument to get really handy criterion. Namely, if we have a class u in the cohomology of X with rational coefficients I'm taking here, actually you could take field coefficients in general, but yeah, sorry, at this point you need the rational coefficients, yeah, with Zn of u non-vanishing, and we know that the pullback of the original class u is vanishing with respect to all maps from the n+1 sphere times p to X. So this is a condition that we have on this cohomology class here, where P is an arbitrarily closed oriented manifold of the appropriate dimensions, so that these two dimensions add up to K, so the degree of the class. Then we know that this weight is 2 or bigger. So this is a geometric way of checking if a class has degree 2. Yes, so this is the thing we want to use, and this is what we want to use to get lower estimates for our spherical complexities. And I want to focus quickly on the case n equal to 0, which is the topological complexity case, because already there we have some consequences with respect to these weights. So if this is generalizing the method that Mark and I used in our argument for symplectic manifolds. So if we have a closed oriented manifold of dimension 3 or bigger, and if we have a degree 2 class, such that the pullback to all by all maps, continuous maps from the 2 torus to M vanishes. So this is the setting that this product of manifolds in this case is precisely just the maps from the 2 torus to M. If we have such a class, if this exists, then the TC of M, unreduced, is 6 or bigger. And another theorem of this style, if we have an even dimensional closed oriented manifold whose TC is not bigger than 4, then we know that the manifold is dominated by a manifold of the form P cross S1, where P is some manifold such that these is of dimension M-1, so these two add up the dimension of M. So we have a degree 1 map, this is what dominated means, from P times S1 to M. So this is the thing we obtain, and this I want to quickly prove. Assume that M is not dominated by such a manifold, so I'm carrying this out here, and that N denotes the dimension of M. We just take some element which is non-vanishing from the top degree cohomology and take the associated 0 divisor. We can construct this U bar 1 times U minus U times 1 is always a 0 divisor here, so a class of weight 1 in the terminology that I used. And we know that by the assumptions, if this is not dominated in this style, then we can compute that, so by the previous theorem, that the weight of this class of this 0 divisor is 2 or bigger. So if we have this, we already have a class of degree 2, but since we are in even dimensions, it turns out that the square of this class is just an elementary computation. This gives minus 2 times U times U. So this is non-vanishing. So we have a class of degree 4, and this means the TC must be 5 or bigger. So this is the way how we can obtain this result here. Okay. Now to the closed geodesics. I don't have that much time anymore, so I will go rather quickly, I think. So first of all, this closed geodesics problem for Finstler manifolds is a highly non-trivial one. You know that every Finstler metric on a closed manifold has a closed non-constant closed geodesic. That's a theorem by Lustanik and Fett from 1951, which was carried out for Riemannian manifolds, but the Finstler case uses precisely the same argument line by line. But already the question if there are 2 or more is a rather delicate one. So I'm introducing this terminology, 2 closed geodesics. I call them positively distinct if they are either don't have the same image or lie in the same O2 orbit, but not in the same SO2 orbit. So just roughly speaking, they are not iterates of each other and they do not lie in the same orbit with respect to the Finstler metric. I don't want to elaborate too much on this. Then not that much is known. Actually, it was only shown in 2007 by Bangert and Long that every Finstler metric on the 2 sphere has 2 positively distinct closed geodesics. Then Rademacher showed in 2009 that every bumpy Finstler metric, this is a generic conditions, which basically means that the energy function is a Morse spot function, which behaves nicely, has 2 positively distinct ones, but this is only generically fulfilled and not by every metric. And then there are certain results by Long and his current and former students. In 2009, they showed the statement for S3. Then Wang showed this on the N sphere for pinched metrics. So we have some curvature conditions involved in there. But yeah, general things, there are so many general questions are still very open in this. So what I could prove then with my approach is that something I will just dropping some technical terms, but you don't be afraid of them. You can ignore them if you're not familiar. We have a Finsler metric on a closed manifold M. So yeah, Finsler metric F of reversibility lambda. This is just some parameter that's kind of measuring the asymmetry of a Finsler metric. This is always 1 or bigger. Like if we have a Finsler metric induced by Riemannian metric, this will just be 1. And we have the flag curvature of the metric. This is the Finsler analog of sectional curvature. So you can think of Riemannian geometry and sectional curvature in this setting. And we know that we have a non-constant closed geodesic, and we let LF denote the length of the shortest one. So what I can then show with these spherical complexities, and by estimating this with the cohomology tricks I just briefly went through, that if we have an even dimensional sphere, so a sphere of dimension 2D, where D is at least 2, so 4 sphere or bigger, and we have that the curvature is positive and bounded from above by 1. And we have such an inequality that F is smaller than or equal to 1 plus lambda over lambda times the Finsler metric induced by the standard metric on the sphere. So the round metric, if we just take this as the Euclidean metric, we get as a unit ball in the Euclidean space. Then if we have this estimate, then we have 2 positively distinct closed geodesics. And what also follows from my energy estimates that are involved in this procedure is that the second geodesic that I obtain in this way is shorter than twice the length of the shortest one. And this is something which is nice because in this results by Long and the others that I mentioned, you don't get any length condition. You know that there are 2 closed geodesics, but the second one could be arbitrarily long and complicated a priori. So here we get this kind of, in this approach, we get for free some length bound. And the same holds for complex projective spaces or quaternionic projective spaces, where this time the projective space of dimension n has to be 3 or bigger. The same conditions, we study the same conditions, but this time we just need a different metric here, which I haven't mentioned. This is the kind of the standard metric, the globally symmetric metric so that becomes a globally symmetric space whose prime closed geodesics have length 2 pi. So it's basically the natural metric on these spaces. Then we also get the same results. So we get some length 2 closed geodesics and the length bound on the second one. So for time reasons, I will skip the last one here. So there's something for odd dimensional spheres as well. That we need quite a bit stricter conditions, but we get some nice estimates as well. Okay, and the proof is then, I will just skip this because so the idea is in general just apply the methods I had before. So estimate these spherical complexities from below by the cohomology tricks, and then show that some critical points are involved in small sublevel sets. And then we can just conclude that they are not iterates of each other because the energy is simply too low. This is the main idea behind this. Okay, so what to do next would be the nice title for this slide. So I just want to mention a few points that you could then do with these invariants. First of all, you could also study similar as in TC or category. There should be equivariant versions with respect to these actions. And this might be interesting because one might get better results because the equivariant cohomology with rational coefficients of this loop space, this you could determine by rational homotopy theory, and this should be a nicer ring structure in many cases. There are already results on closed geodesic using equivariant cohomology by Hingston, Rademacher, and others. But the question would be if you can, yes, incorporate this in this approach as well. Then, of course, I'm just studying variational problems in general, which are invariant under group actions on these loop and sphere spaces. And on the loop spaces, one question would be if you could apply this type of theory in greater generality to periodic Reeb orbits. So these are critical points of action functionals on contact manifolds, which generalize the case of closed geodesics on the unit tangent bundle as a contact manifold. So these are Reeb orbits closed geodesics are orbits of geodesic flows, and this is a special case of Reeb orbits. The problem here is that the action functional of general contact manifolds behaves very bad. Namely, it's not Palais-Smale, it's unbounded, and it's really behaving badly. And there are some approaches on variational theory of these functionals as well. For example, by Abbas Bari, he carried out some variational approach to these functionals, trying to deal with the lack of Palais-Smale and to find some approaches to these functions as well. So it would be maybe worth studying this. Then, of course, I've just studied functions on loop spaces, but I've had these invariants on all sphere spaces. So the question would be if there are higher dimensional applications, for example, so for n bigger than 1, so maps from spheres to manifolds, for example. And for example, there is the energy functional for spheres in Riemannian manifolds. The problem is that, so the critical points of this are minimal surfaces of metrics, but the problem is here that this function is also not Palais-Mail. So one also would need to work a way around the Palais-Mail thing, and actually one might generalize this in a nice way or find nice perturbations of this. There are also approaches in the literature that have been taken. So this, this would be an open question here. Then if any one of you has any ideas of what to do with these things, or if you have an idea for a potential application or see a connection to your work, I would be really interested in hearing your ideas. And so just feel free to contact me. I would be happy to discuss these things with any of you. Okay, that was all I wanted to say. Here are just the two papers, one from last year, one from this year, that my talk was based on, and basically summarized the main results. I will put the slides on my website when I'm back in my office next week. And yeah, if you want to contact me, you can also just send me an email. Yes, that was what I wanted to say, so thank you.
Thank you very much, Stephan. This is a very nice work.
Thanks.
We can... there are some questions, I guess. Mark, I think it has one question.
Well, can I ask two questions?
Hi, Mark.
Sure.
So the first one was, you have this class Zn of U in the mapping space of the sphere.
Yes.
Is Z0 of U the associated zero divisor? So 1 cross U minus U cross 1.
So here it is. If this is, yes.
And so is it possible that Zn of U is always non-zero?
It might be. It might be. I mean, I don't know, since also this, I had this statement that in the for n equal to 1, we had, I had this from the Jones theorem, but there the assumption was that X is simply connected. So there might be some connectivity issues. I'm not sure about this. But it might be true that that's always non-vanishing, but I couldn't find a general answer to this.
And then the second question was, you had these nice applications to oriented manifolds. So if TC is at most 4, then it's dominated.
Yes.
Yeah. I just wondered if you'd thought about the Petar's question that he spoke about yesterday, TC3, and whether or not you can say anything about that using these methods.
Yes, I can, and I have put this is a result I haven't put on this slide. If I prepared the slide before I heard Petar's talk, otherwise I would have put it in. I can say something about TCM less than 3, because then I can say that if it's, so not forgetting about this even dimensional assumption, if we just have a closed oriented manifold of dimension 3 or bigger, I think. If TCM is lower than or equal to 3, then we must have that it's either dominated by such a manifold or it's a rational homology sphere. So one of the two always holds, and that's yeah.
So if you could show that the Wu manifold wasn't dominated by manifold cross S1, then you've answered one of Petar's questions. Right.
Oh, yeah. Yeah, the problem is I'm not familiar with the Wu manifold, so but this might be worth thinking about, definitely.
Okay, thanks.
Thanks.
Okay. Are there any more questions?
I have a question. Jesus, can I ask?
Yes, sure. Go ahead.
Stephan, exciting talk. Very nice.
Thank you.
Congratulations. Just wanted to mention, I mean, one possible idea to deal with this issue of constant loops and multiple loops. I mean, I had this idea many years ago, but nothing was done. So one possibility is to take this energy functional and convert it into a closed one form. And by doing, by taking logarithm of it on the complement of zero are constant loops, right? If you remove constant loops, then it is positive. So you take log and then differential. D log of this is a closed one form. It has the same critical points, but it is invariant under iterations. So, I mean, if you, what I'm saying,
okay.
it's a little bit naive, but just because you ask us to give you ideas.
Yes.
So this is one of these ideas which I think may potentially work. Instead of function, to look at closed one form and on some quotient of the space of loops by a multiplication, and look at, but I mean, enormous technical difficulties, of course.
Yeah, I imagine.
Yeah, so just a general idea.
Thanks. That sounds extremely interesting. Yes.
Okay, Asia.
Hi, Stephan. Thank you for the talk.
Hi.
Do you have an example of a simplicial, motion planning algorithm for the case which corresponds to one spherical complexity? Or is it a hard question or an easy one?
No, I haven't. I don't have explicit sections here, but yeah, this would be interesting in general. This is, yeah, I haven't studied any concrete examples there, but yeah, then this doesn't mean, I mean, I was focused on this variational application here, but this might be also, there might be nice ways to find explicit sections here, sure.
Okay, thank you.
Any further question? Maybe I have one comment that might be related to Asia's question, namely the simplicial approach to topological complexity is based on, of course, the simplicial approach to continuous maps and homotopies through contiguity classes. And there is this work of Bloomberg and Mitchell, I think, where they generalize that result and basically give an approximation of the homotopy type of the space of maps, not of single maps, of the homotopy space of maps by the, more or less the same idea. I don't really know the detail this thing, but that might actually give you a way to try to discretize this problem and try to find then algorithms for finding spherical motion planners.
Nice, I wasn't aware of that. Bloomberg and Mitchell, you said.
Yep.
Okay. Thanks.
Yeah, I can send you the reference. If you send me an email, I'll send you the reference.
Oh yes, sure, thanks.
Okay, are there any more questions? Well,
yeah.